Hi there. In this video, we're going to talk about general and particular solutions to ordinary linear differential equations. So first, we'll start out with one of the simplest differential equations that we could solve for. And if I know that the derivative of a function y is equal to x squared, well, then if I integrated, then I would get back to the original function y. So I'm finding the antiderivative here, basically. So I'm going to integrate both sides of this equation. On the left side, I would just get the original function y. And on the right, for here I have y prime equals x squared. So the integral of x squared would be 1/3 x cubed plus the constant c. So that constant of integration that we get when we integrate like this in an indefinite integral, and we call that a parameter in differential equations. And when I have a parameter that is a constant like this, it's unknown, then we would call that the general solution. If I had some initial conditions, we call them, for this differential equation. So for example, what if I knew that y of 0 equaled 5? Well, suddenly I have some values that I could plug into my general solution that would allow me to solve for that parameter, that constant of integration c. So I'm going to do that here to get a particular solution. So if y of 0 equals 5, then that means that x is 0 and y is 5. So I plug that into my general solution, and let's do a little simplifying, and I get that that constant c is equal to 5. So now I have a particular solution, y equals 1/3 x cubed plus 5, in addition to that general solution. So there could be, as the initial conditions change, then I would get a different particular solution. So this general solution, it really can, if I look at all the possible values of c, I get a family of solutions from that. So that there is a particular solution, and that's how you'd find it when you're given initial conditions. Now let's take this to an application example where we look at acceleration and velocity. So let's say I have, I'm modeling the motion of a particle. And so I have this position function, x is equal to f of t. So it's some function of time that tells me where the particle is at a particular time. If I were to take the derivative of my position function, I get the velocity of my particle. So v would be equal to dx dt, so the derivative of x with respect to t. If I take the derivative of that, then I get my acceleration function. So the derivative of v with respect to t, or the second derivative of the position function, would give me the acceleration. And I can work my way backwards as well. If I had the acceleration, just like we did with the last example, if I start integrating, I can get back to that velocity function. And then if I integrate it again, the position function. So let's say I take a particle, I apply a constant force to it, and so the acceleration is a constant. We'll call it a. So dv dt is a, is one way of representing that. If I integrate that function, that will get me my velocity function. So the integral of that constant a would be a times t plus a constant of integration. We'll call it c1. Now, if I had some initial conditions for this scenario, let's say v of 0 is equal to what we'll call v naught. So that's a v sub 0, often called v naught. If I plug that into my function v of t equals at plus c1, then I get v naught equals a times 0 plus c1, which means that c1 is actually equal to v naught. So my position function is at plus v naught. So if you've taken some physics, that formula might look kind of familiar, and you can kind of see where we derived it from. Now, that gives me my velocity function. To get to the position function, I would want to integrate this. So if I take the integral of at plus v naught, then I would get 1/2 a t squared plus v naught t plus another constant of integration we'll call c2. If I have some initial conditions for the position, let's say x of 0 equals x naught, then I can plug that into the equation as well. So x naught would be equal to 1/2 a times 0 squared plus v naught times 0 plus c2. So everything zeroes out on the right. I get my constant c2 is equal to x naught. And I get a position function, x of t equals 1/2 at squared plus v naught t plus x naught. So it should look kind of familiar, and this is kind of one of the ways that we can apply differential equations and solving them to some physical examples. Now let's take these equations and solve a problem with them. So let's find the position function x of t, given that a of t is equal to 0, v naught is 5, and x naught is 15. So I've been given the initial conditions, so I can solve for those parameters c1 and c2. And really, I'm just going to take that equation that we derived, and I'm going to plug everything into it. So x of t equals 1/2 at squared plus v naught t plus x naught. Plugging all of my values in, I get 1/2 times 30 plus t squared plus 5t plus 15. And I can clean that up just a little bit by multiplying the 1/2 times 30. And oh, I left it off there. This should be 15t squared plus 5t plus 15 to give us our position function. All right, so just an example of how we can start to apply these methods of differential equations and initial values. One other thing we want to talk about in this section is slope fields. A slope field, sometimes called a direction field, is a visual tool that we can use to represent all the solutions of a first-order differential equation. So if I have a differential equation dy dx equals some function of x and y, every point xy in the slope field is associated with the short line segment that we'll take a look at, which is the slope at that value of dy dx. So the slope at each point xy is given by evaluating the derivative. So it may be kind of hard to visualize, so let's look at an example. And Desmos is great for doing slope fields. I will give you a video down below, or a link down below where you can create slope fields pretty easily with Desmos. So this example says identify the slope for the solutions to the differential equation at 2, 1, the point -1, -1, and 4, 0. So I have this differential equation, dy dx equals x over y. And so if I wanted to evaluate it, each of these points, let's say we'll take the first one, 2, 1. So dy dx would be equal to the x value divided by the y value. So 2 divided by 1 would give me a slope of 2. So at this point, 2, 1 on the slope field, I would have a little line segment with a slope of 2. Let's do the other two, and then we'll look at the graph to see what that slope field actually looks like. So if I plug in -1, -1, well, now I'm doing x divided by y, so -1 divided by -1 gives me a positive 1. So the slope at that point would be at an angle of 1, so just like the line y equals x. And the last one, 0, 4, if I plug that in, 0 divided by 4 gives me 0. So I have a slope of 0, which means I should have a flat line at that spot. Now, if I were to pull up Desmos and graph this, this is what the slope field looks like. So you can see at each integer point along here, it gives me a little line segment at an angle that's kind of representing what the slope is there. So looking at the 3 points that we just found, if I go to 2, 1, I can see there's a line segment that's kind of steep, has a slope of 2. At -1, -1, this one's a little bit less steep because the slope is a little less at 1. And then the last one we looked at was at 4, 0, 4. And so you can see how I have that flat line there for a constant. So that's what a slope field looks like, and it just gives us an idea of what all the solutions, if I were to kind of connect these, I get an idea of what the solutions to this equation might look like from these line segments.